So it will not cover too much.
Yeah. Maybe wait for 2 more minutes.
Yeah, of course.
Yeah. Maybe we start to introduce. Okay. Hello everyone. Welcome to the 2022 Loess ECR workshop. So in the last 3 days, we already have 3 very good sessions. Today, we will continue our workshop, and the topic will be about dust modeling. Please allow me first to introduce the keynote speaker of this session, Dr. Albani. Dr. Albani has obtained his PhD degree in University of Siena in 2009, and then he has been a postdoc researcher at Cornell University in USA, University of Cologne in Germany. He has also been awarded as Marie Curie Fellow in France. Now, Dr. Albani is an associate professor at the University of Milan in Italy. Dr. Albani has been working on dust and climate interactions with a highly interdisciplinary approach, ranging from experimental research on ice cores to most recently numerical modeling of dust cycles using Earth system models. Dr. Albani has published 40 papers in international peer-reviewed journals, and he has been one of the leading researchers, especially in the field of paleodust modeling. So now let's warmly welcome Dr. Albani to give his talk. Please, Samuel.
Okay, thank you very much for your introduction, Yue, and also thank you a lot for inviting me. It's a pleasure to give a talk into this venue, and also thanks for all the people who are willing to listen to this talk. So this is a bit of an outline of the talk I'm going to give. So first of all, I'm going to introduce a little bit or review a different perspective for looking at mineral dust. So as a tracer and as an active agent in the climate system. And then I will move on to introduce a bit what climate and Earth system models are, and move on to a few key aspects of modeling of the dust cycle in particular, and modeling dust feedbacks on the climate system. Later, I'm going to talk about how we can compare and use in a complementary way model simulations and observation of the dust cycle. And the last part of the talk will be dedicated to actually the recent advances, as the title suggests. In particular, I try to focus on 4 specific aspects of the dust cycle, so particle size distributions, dust mineralogy, optical properties, and paleodust compilation. So all of these are few aspects that have seen some improvement in the last few years. Some of which are also perhaps directly relevant to those in the observational and also in the Loess community could find of interest. So here are just a few images which we can relate to the dust cycle. So you see the red dawn in Sydney, for instance. You see dust storms. You clearly see some dust transported over the ocean as seen from the satellites, and you can see specific landform associated to the Loess in North America and in China, of course. Now, in general, we can talk, or people have talked about the global dust cycle, as you see here. And in particular, we have a mass budget, which can be estimated, but basically the most important thing is that there are several processes that start with basically erosion of the surface that cause emission associated with several specific processes, atmospheric transport, potentially transformation, and deposition back to the surface on land and the ocean. And during this cycle, there are several transformations and several impacts that dust have. Now, as my first point suggested, I'm trying to look at dust here as both as a tracer and an active agent of the climate system. So these two complementary views are highlighted here in extreme synthesis. Why we talk about dust as a tracer? That is because if we take the most idealized structure of the global dust cycle from the slide, for instance, that I showed you before, we can identify three key steps, which are emission, atmospheric transport, and deposition. And each of these essentially depends on specific processes, which are climate influence in a way. Also, as we have seen, dust is an active agent, meaning that on different time scales, dust can exert feedbacks on the climate system. And this happens while dust is airborne, as an aerosol, because it can provide, or it interacts with radiation, it interacts with clouds, with atmospheric chemistry, but also after deposition. In fact, dust deposition can cause snow darkening and is important for the biogeochemical cycle in the ocean and on land. And in addition, if you look at longer, very long time scale, dust can also be seen as a geomorphological agent impacting landform. For instance, as you know very well, the formation of the creation of Loess. Now, going into a little bit more of detail concerning dust as a tracer, well, we can say that dust can provide composite indication on the processes that control its emission, transport, and deposition. So in a sense, this is very similar to what the yesterday's guest, Gabo Rivari, mentioned about the difference between indicators and proxies in a way. So I think these slides happen to report the same kind of terminology about indications. So in particular, we can talk about the composite indications concerning the climate and environmental condition of the source areas, of atmospheric circulation patterns on wind fields and precipitation, each associated with respectively emission, transport, and deposition. Of course, this is most typically the things that people looking in the paleodust observational community tend to look at. And this truly holds for this, but also it is interesting potentially for people working in the modeling community, because in the same way could be possible to use modeled or simulated dust tracers and indicators of how well all the processes controlling the dust cycle in the models are also represented. Particularly in models, the explicit representation of the dust cycle is also can also be considered an example of process-based modeling, so which allows a more or less direct comparison between simulated and observed variables. In particular, if we're talking about dust deposition as an interesting fact for this community. Now, the other hand of the coin, so the dust as an active agent. This is because dust affects climate in several ways by scattering and absorption of solar and terrestrial radiation, which is also known as direct and semi-direct effects. Dust can act as a cloud condensation and ice nuclei, therefore influencing cloud albedo and lifetime, and these are complexly known as indirect effects. Also, dust can act as a carrier of limited nutrients for important ecosystems, such as iron for the ocean, high nutrient load chlorophyll areas, or phosphorus for the Amazon basin. And these are examples linked to the biogeochemical effects that dust can have. In addition, as already mentioned, dust deposition on snow and ice can cause snow darkening, influencing clearly the albedo and enhancing snow melting. And while airborne in the atmosphere, dust can act as a surface for heterogeneous chemistry reaction, some of which also can impact for instance, the iron processing, which also have impacts on dust ability to act as a biogeochemical agent. Okay, so after this brief review of different and complementary ways of looking at the dust cycle, let me delve into the matter of climate and earth system models. So basically, we can think of a few key aspects that we need to take into account when trying to represent our planet by means of a model, of a mathematical model. We have, first of all, an energy balance to account for. So we know that the energy of our planet comes essentially from the sun in the form of electromagnetic radiation. And basically we have some basic conservation law of physics, and we can make very simple earth balance, energy balance models like it's represented here. But of course, the situation is more complicated. The Earth is not just a single point. It's spherical, so there are differences in the way energy from the sun is distributed. And we know also we have an atmosphere, which imply the presence of the greenhouse effect because of its composition, as we all know. And so, of course, we need to try to represent these elements. At the same time, we also need to represent the dynamics of the atmosphere and of the ocean, which are also facts, or also basically including some of the elements that we associate with climate. Now, this is basically achieved in these models by writing these complicated, huge computer programs in the end. But we can ideally decompose basically the parts of this code into two main parts. The first is what is called the dynamical core, which contains the explicit solution of the equations that describe the flow of air masses three-dimensionally in the atmosphere and in the ocean. And this is complemented by the suite of physical parameterization, which are a representation of subgrid scale processes, as well as many other processes, including, for instance, radiation transfer. And the difference is that while the dynamical core describes the dynamics in a 3D environment, physical parameterization tend to be calculated locally. So this is why I indicated the 0D problem, or in a few specific cases, a one-dimensional, for instance, when we are talking about parameterization of convective processes. So here you see basically a representation of a three-dimensional grid covering the atmosphere. You can see highlighted a few subgrid scale processes like clouds. And on the right side, you can see a representation of a single atmospheric column. And you see how the interaction of incoming solar radiation is evaluated at each specific level. And we will see a little bit more of this later, but I think this can give already a vague idea of the key components of a climate model. If we go to, if you start looking at the dynamical core of climate models, basically this is a set of equations. These are often called the primitive equations. Basically, these come from fluid dynamics, and they represent basic principle of physics, such as the conservation of momentum, so Newton's second law of motion. You see three equations because these are the three spatial dimensions, and then you see the equation of state, the gas equation, the conservation of energy, and the conservation of mass. So each of these terms basically accommodates specific components which are peculiar or typical of the atmospheric environments as well. The formulation that you see here is one of many possible. There are different ways of the degrees of approximation of writing these equations, of course, but this is a kind of simplified way, and I think it just makes the point of what kind of physical aspects are included in this dynamical code. Clearly, one specification that maybe is worth doing is that in general, when people think about the property of the fluid in motion, how they vary with time, there are two main strategies that have been devised. One is the Lagrangian representation, which focuses on the prediction of the coordinates in time of a parcel in movement. So basically, this is evaluating or predicting the motion of single particles, and many particles are needed to be simulated in order to define the property of a fluid. So this kind of formulation is typically used for contaminant dispersion problems rather than for climate models, which instead use typically the Eulerian form and describe the motion of air, and as well as properties like tracers, but basically by dividing the space in small portions and evaluating the fluxes of air in and out of these. And basically, mathematically, this involves a spatial derivative, essentially. Then there are clearly, or there are other hybrid forms, like as the semi-Lagrangians, which are used in climate models only for tracing. But typically, this is the Eulerian form is the one that is mostly used, and the one that were used in the equation depicted. Now, I don't want to go into many details, but just to give you an idea of how we can solve this equation. Because one problem of that set of equations is that they are nonlinear equation, partial derivative equation, and they do not admit an analytical solution. Therefore, discretization and numerical solution is required. So if I take, for example, the first equation, so the conservation of momentum for the x dimension, and we simplify in a very at the minimum, we can see that we have basically a partial derivative with respect to time and a partial derivative with respect to space. And discretizing basically means subdividing the time axis in discrete steps and translating this derivative into a set of differences and multiplication. So, and the same can be done with space. Here is just a two-dimensional grid, but just to give an example. So basically, this derivative is translated in a gradient somehow. And if you see this, I highlighted here in red, this tau, it's the time index. And you see that in the end, you have something which is tau plus 1, which is the future time step. And tau minus 1 is the past, and tau is the present. So basically, if you rearrange the two terms of this equation, you can clearly derive an equation which represents your calculation, your forecast. So this is a very simple, idealized representation, for instance, of the 3-point center different approximation in time and space. This is just to give you an idea of how these equations are solved numerically by models. Now, an implication of this is that if we have to apply the discrete grid to the space, we can have certain features of the climate system, of atmospheric circulation in particular, which we can resolve. So for instance, if you see this vortex, we have a number of pixels, if you want to describe it this way, which is enough to describe the features of this element. On the other hand, for much smaller structures, we have basically, they happen on unresolved scale with respect to our grid. Therefore, we require specific physical parameterization to represent implicitly this aspect. And so the last that I mentioned are the first type of physical parameterization that I mentioned. So those are the closures category. So there are subgrid scale processes not represented by the grid, such as convection, turbulence, etc. Then we also have other types of parameterization. So those related to microphysics, such as radiative transfer, the representation of precipitation, clouds. And we have all those involving interactions, which includes exchanges among system component, for instance, air-sea interaction, air-land, the carbon cycle, chemistry, and aerosol. We have seen quickly that there is a conservation of mass, the continuity equation, which was part of this primitive equation. A similar formulation can be used to describe a tracer, so an element which is affected by the atmospheric dynamics. Basically, this is stating that the variation of the concentration in time of a given tracer is equal to the fluxes in and out of a given grid cell that we are analyzing, and it should be zero unless there is a net local source term. Basically, this is the balance between the sources and the sinks, so the inputs and the outputs. And this slide is basically talking about the generic tracers, and I show some examples, so water vapor or CO2, and you can see different aspects. If we talk about aerosols in particular, the net local source term should include emissions, which could be calculated by the model, or they could be prescribed, for instance, anthropogenic emission. And this will contribute to the input or sources. But then we have the sinks or outputs, such as gravitational settling or wet deposition. So basically, if we want to build a representation of the dust cycle in the dust model, we need to implement a tracer like this, which would be described by an equation like this. And most of the modeling work would be to define all the aspects of this naked local source term. Clearly, climate models have been developed since World War II, and in particular, by the mid-70s, they were established coupled climate model, including a representation of the atmosphere, the land surface, ocean, and sea ice. And these have been evolving in complexity with time. Here you see the first, second, so these are the IPCC assessment report. So this column or the height of these cylinders represents the complexity of representing each component. But you also see that with time, additional components have been added, including aerosols, carbon cycle, dynamical vegetation, and so on. So in the terminology, essentially, when people talk about climate models, they talk about the basic part of it, whereas Earth system models are those that include these other aspects of the of the climate, such as the carbon and nitrogen cycle and aerosol in particular. And here is just a slide, the comparison taken from the last IPCC report, comparing what were climate models at the time of the first assessment in 1990 and at the time of the last assessment. So basically, we now have global Earth system model, which can have a horizontal resolution of about 100 kilometers, or regional climate and Earth system model, which can resolve a 25 to 50 kilometer grid cell and represent all these aspects. So atmospheric circulation and the ocean, radiative transfer, land physics, sea ice, in some cases atmospheric chemistry, land use and land cover, and in many cases land and ocean biochemistry, and also aerosol and cloud interaction, basically. So this concludes a little bit the general overview about climate and Earth system models. So you have hopefully a little of an idea of what kind of tools they are. Now, let's move on to modeling the global dust cycle in particular. So this is a schematic representation, but basically, as we said, we need to be able to represent these basic aspects. So emission, dry deposition, wet deposition, as well as some of the interaction with radiation, short wave and long wave, with clouds, also snow darkening and biogeochemical cycle impacts. So first of all, one aspect that I mentioned is that we need to have an atmospheric tracer. In general, aerosols, though, have different composition and dimension with implications for their atmospheric lifetimes, their impacts on radiative transfer and cloud microphysics. so important that in a general strategy for the implementing or building a climate model, different aerosol, for instance, sulfates or black carbon or dust are considered. Not only, we need to take into account the variability in the particle size distribution if this is a characteristic of a specific aerosol. And we know, for instance, that dust has a wide size distribution ranging from submicron to several tens, at least, of micrometers. Therefore, we cannot only focus or use a bulk representation with a single tracer for dust, but we need several tracer for dust, each of one representing a different size class or size mode. And in general, there are two main strategies that have been devised in the community to represent the size distribution. The first category is represented by sectional scheme. So there are basically a number of bins, each representing a size class, and you can have something between 4 to 10 bins, size classes, in models, in global Earth system models. Or the other strategy is to adopt model scheme, which are defined by assuming a log normal distribution and specifying a mode and a standard deviation. And then basically you can take into account the number, both the number and the mass of these tracers in order to evaluate the evolution of the mode. So how the size distribution evolves in the model. And maybe this is more clearly represented here. So you can have sectional scheme using size bin. In this case, we have a representation of the number of particles with respect to size. But as I mentioned, also the mass, or let's say the volume, are tracked, which allows then, by the combination of the two, to evaluate the evolution of the size distribution. Now, typically, only relatively small particles are considered, though. So with diameters below 10 micrometers or 20 micrometers. So this is because these are the particles that have the longer atmospheric lifetimes, and therefore also the better potential for long-range transport, and have the most important interactions with solar radiation. Now, concerning dust emissions then, once we have defined how we represent dust in the atmosphere, we focus on the other aspects. So dust emission scheme range from minimal parameterization to more physically based approaches. The latter clearly could be more realistic, but they are more computationally expensive, and they may depend on a larger number of parameters that are themselves uncertain. So there is per se no better way to do things, but there are different approaches. In general, dust emissions are caused by wind erosion of partially vegetated, arid or semi-arid areas with different mechanisms. And dust emission scheme basically account for these aspects. So there is the key aspect is to evaluate when the surface wind is above a specific threshold. So all dust models have this component, whether it is the wind speed itself or it's the wind friction velocity above the surface. And then there are these other four categories of aspects which are accounted in different ways in different models. So one is vegetation cover, which could be included as a threshold value above which there is no dust emission, or it's a scaling factor. So inhibition is similar. The soil moisture is another aspect, which can come from the land model itself. So it's coupled representation, or it's a function of precipitation from the atmosphere, for instance. Then there is a point of sediment availability or erodibility, which has caused the use of some search functions to represent again, sediment availability, and is typically based on geomorphological features. And finally, there is a soil type, which can come in as to impact the threshold for wind speed, or impact soil moisture itself, and it's accounted for depending on the mineralogy of the soil type, of the particle size of the dominant soil type. So in general, in all these prognostic dust emission scheme emissions, so the vertical flux are a function of wind speed above the given threshold, let's say. The threshold itself and or the scaling of dust emission fluxes have some dependence on the surface properties. So this is perhaps more clearly represented. You have these basic, so the dust emission is typically assumed to be proportional to the cube of wind speed when the wind speed is above a given threshold. And this is scaled by, so the wind threshold can depend on the surface properties. And there is a scaling itself generated by dust lifting, so transfer of momentum, or the sediment availability. Now, this is just an example of dust emission schemes, two particular dust emission schemes that were compared in this paper, just to give you an idea of how different specific aspects can be combined. But as you see, in the end, both these schemes have a threshold friction velocity, so the wind above a given threshold, which appears, and in the end, there is a vertical dust flux. Now, another aspect that I haven't described before is this seed. It was this tuning factor in this that basically allows linking the emission, the relative emission calculated by parametrization on the spatial scale of the modest grid to match a global property, for instance, the global IOD. And basically, this is allowing to going from the micrometer scale represented by these physical processes to the grid cell of 100 kilometer scale. Finally, we need to account for dust deposition, which can come from wet deposition, so from in-cloud or below cloud scavenging and precipitation. There is gravitational settling, which is clearly size dependent. And the combination of all these determine atmospheric lifetime, so the residence time. Coming to the dust feedbacks on climate, we see this aspect that we already briefly mentioned before. But let's go into the dust interaction with radiation first. So different aspects of aerosol determine their net effect on atmospheric radiative balance. So in particular, in the case of dust is both scattering and absorbing solar radiation, depending on the wavelengths and the particle size. And also, so compared to these plots, dust can be either cooling or warming, depending on the albedo of the underlying surface and depending on the particle size. Which makes the treatment of dust atmospheric interaction with atmospheric radiation particularly complicated with respect to other aerosol types. Also, dust absorbs and scatters long-wave terrestrial radiation, which makes all these interaction even more complicated. So in two words, let's say that the dust interaction with radiation in the model are evaluated by a set of parameters, which basically are multiplicative factors that determine the amount of transmitted component of the incident radiation, and the one which is absorbed, and the fractions which are backscattered or forward scattered. And these optical properties in practice depend on the wavelength of radiation and the size and composition on the particles. The other type of interactions are aerosol cloud interactions, so the indirect effects in the atmosphere. And this is because aerosol particles, including dust, can act as cloud condensation nuclei or ice nuclei, resulting in a larger concentration of smaller droplets, which cause an increase in cloud albedo and an increase in the cloud lifetime associated with delayed or reduced precipitation. So state-of-the-art models are more and more incorporating these kind of effects in the climate. Now, the other aspects is dust impacts on biogeochemical cycle. So this is, in this case, it's represented how dust is basically impacting the ocean biogeochemistry through its ability to carry iron, in particular bioavailable iron, which can relieve the nutrient limitation for certain communities. And with the presence of ocean biogeochemistry model, it is possible to couple dust deposition, and in particular make assumptions or try to represent explicitly the fraction of bioavailable iron component in dust, and therefore couple these two processes in a global Earth system. Now that we have described already how we can represent, at least in very general terms, dust in Earth system models, let's try to see how we can make use of this and also compare with observations. In general, thinking especially of present day, we can use remote sensing observation, whether ground-based or from satellite, to have some constraints on the global dust cycle. So we have total extinction or dimming in the atmospheric column, and by extension, we can evaluate the dust load. And we can also have information on the vertical profile of dust. In situ measurements, again, ground-based or airborne, can provide information about dust atmospheric concentration or dust deposition. And then we have natural, for instance, I think of snow in particular, but also paleoclimate archives, which can provide information on dust deposition or paleodust deposition in certain conditions. Here is just an example of how we can compare model simulation from different models with observation. For instance, this is the annual, the typical annual cycle of dust deposition at Barbados, which has, so it's the average and the standard deviation for a very long, over 50 years dust record, or this is the dust deposition network from current climate. And this is so the location of the station, and this is just a scatter for comparing model and observation. So we see that in general, model can capture the order of magnitude of the specific aspects of the dust cycle that we are able to sample somehow, in this case, measuring dust deposition. Coming to paleodust observation, we can use, and it has been used, several natural archives. For instance, ice cores, marine sediments, and of course, Loess paleosol sequences. The quantitative variable which is used to compare on the same scale all these different archives, as well as climate models, are dust mass accumulation rates. So if we are in the conditions to derive these accurately from this kind of archives, then we can use this kind of information to compare with climate models. Now, coming to constraining the dust budget, basically, we have a tight relation between the particle size distribution and the mass budget of the dust cycle. As you see here, this is a modern dust deposition. The higher the dust deposition, it is associated to larger particle size distribution, obviously. And this is because there is this idealized representation that most of the larger particles basically are removed within, let's say, 50 kilometers from the source areas, and then they tend to remain in aloft only the smaller particles, which can undergo, in general, long-range transport. So one implication for this is that dust mass accumulation rates from paleoclimate archives need to be representative of large-scale deposition if we are to compare this with the climate models, which have a grid cell of, let's say, at least 100 kilometers. Now, there are several ways we can try to not only to compare model and observation, but try to make inferences. Or, for instance, in this case, at the large scale, it was possible to use observational constraints on dust provenance to scale dust emissions. So we have the known source areas. We can simulate emissions from those source areas, and then we can basically use a sort of a data assimilation process. If we have data which we can link by means of, for instance, provenance studies to specific areas, then we can use this to derive the proportion of, to evaluate the proportion of how each source accounts for the dust, which is either deposited or present in the atmosphere. We could also use models to interpret our observations, for instance. So in this case, the question was, how much is a paleodust record representative of the large-scale features of the dust cycle? So in this case, this was done by investigating the large-scale correlation in both space and time, so across glacial interglacial cycles. So the higher correlation, meaning that a particular site, for instance, the Vostok ice cores, were representative of a large, the same amount of dust in a larger area. And the state of the art implies that there are still significant uncertainties in the mass budget and therefore impacts of the global dust cycle for present, therefore pre-industrial and paleoclimate conditions. And so this plot has given an idea of a number of studies which also had focused on paleoclimate conditions. So we can compare the current or pre-industrial state with the last glacial maximum. You see that there is a huge amount of variability in these estimates, and also in the estimates of the dust impacts on the radiative forcing, for instance. So this is another example of the same. So here I mentioned the PMIP, so the Paleoclimate Modeling Intercomparison project, which uses simulations of paleoclimate condition over system model as a general idea to validate these models, the same that are used for the future climate projection. And you see here there are three different reconstruction of dust deposition flats for the last glacial maximum, and they substantially differ. If you look, they were done with different strategies through data assimilation, by only model, or by cravings, or the statistical interpolation of observation. So basically, the main thing is that we need more observation in order to better constrain the dust cycle, and they need to be also used or incorporated, aggregated in a meaningful way to try to reduce these kind of uncertainties. Now, let's come to the last part. I'm a bit late, but I have only a few slides. Hope you don't mind. So I have recent advances. So what are the main evolution in the last few years? The first one concerns particle size distribution. So recent observations showed larger particles than previously assumed could be retained for long-range transport. So now there is a trend in the modeling community to try to expand the model size range, although there are still problems with the lifetime, which is still too short. But anyway, there are theories and there have been implementations of trying to include larger tracers and have theories for emission of larger dust particles and beyond the 20 micrometers at least. And this could be useful if we want to try to compare proximal dust sinks, as could be information we can derive from the Loess with climate models. A second aspect of interest of activity in the last years is the explicit representation of dust mineralogy. So a few Earth system model has started incorporating explicit dust mineralogy, which bears implication clearly for interaction with radiation, with clouds, for biogeochemical cycles, and interesting for this community for provenance studies. In particular, now there is this ongoing project, it's called the MIT, which is trying to measure from the International Space Station, essentially the mineral composition of dust-forming areas, because all these efforts rely on the FAO, FAO soil maps, which bear significant uncertainties. And as you can see, also there are problems in the model in simulating the dynamical range of This is an example of Cowley-Knightley light ratio from observation. Probably because we miss the spatial variability at the emission sites already. And both size and composition bear also implications for the dust optical properties. And there are also updated experimental studies which have caused a better understanding or more accurate measurements of actual optical properties. And unfortunately, there was still around in the community the use of optical properties which were outdated, which caused basically some problems. Here you see there are several studies. The oldest one and the newest one are causing a reevaluation of the overall direct impacts of dust. And you see with time, it's been reduced, the overall impact, which is getting closer to zero. A note of caution is that this doesn't mean that dust doesn't have an effect on global radiation. In fact, the net zero is hiding significant regional impacts of opposing sign, some of which can have important implications. Because, for instance, they can try to strengthen certain gradients, which is important for the monsoon systems, for instance. As you can see from here, so basically this is an example comparing the old dust, which was too absorbing and too fine in the size distribution. And if you put this, if you change the optical properties, you have a completely opposite impact of dust on the West African monsoon system, which is enhanced by the presence of dust if you use most recent observation and coarser size distribution, but it was actually reduced in the other case. So this has also important implications. And finally, let's come to the point of paleodust compilation. Here I already mentioned dust mass accumulation rate, which were used since the seminal work of Hoffel and Harris on the dirt map to compare paleodust data in model simulation. So there is new work I've also been trying to carry on, which is focusing on time series instead of just time slices, and of side resolve instead of bulk dust mass accumulation rates, basically. So this could be a better way to be able to compare with models, taking into account the size distribution, and therefore also providing a better representation of the dust that we can expect to be in the atmosphere, with all the implications this has for impacts of dust with radiation and so on. And last, concerning the loss in particular, clearly it would be very, very useful to have reliable estimates of dust mass accumulation rates and how this varies with time. But there are a few caveats, I think, to this. For instance, the geomorphological setting is important because of what I mentioned about the large-scale representativity. So there are certain geomorphological settings which are useful, very useful, or prone to be relevant to provide dust mass accumulation rate. In particular, I think of Loess terraces, and others which would be not so useful in this sense, even if they can be very useful for other purposes. There is the matter of spatial scales, clearly field sampling protocols, dating methods, all these. And in particular, another important thing is to try to understand the post-depositional processes or the presence of a regional stratigraphy that can be used to assess the spatial representativity, because in the end, and I see here, we want to have to be in the conditions which are in which the dust mass accumulation rate is as close as possible to the deposition flux, because this is the parameter we want to estimate. We can compare to climate model simulation. So when these conditions are most closely met, this is where we can really use information from Loess paleosol sequences to compare with this. And with this, I end my presentation. Thank you all for your attention. This is my email in case you have more questions that you want to ask beyond this, the time which is reserved now. And I stop sharing here.
Thank you. Thank you very much, Smil, for your great talk on dust modeling. I will say very informative. You present a detailed review on how to model climate system and then how dust cycle is involved and represented in the model. You also show some recent advances in dust modeling. So now I think we come to the interactive discussion part of the session. So please raise your hand or just unmute, and you can also leave the questions in the chat box if you like, or you can send the question to me and I can help to read. Is there any questions? Okay, I see Professor Lu. Please, Professor Lu.
Yeah, Samuel, thank you very much. Very nice talk. Very nice lecture. From the numerical modeling side, where and how should we strengthen the observations to obtain the very useful data to understanding the dust process? What's your think? What's your idea?
So what kind of observation can be most useful for comparing with the or representing dust processes? Did I understand?
No, I mean no. I mean where and what work we should strengthen in the future to compare with your modeling results.
So I think
what we should do. Thank you.
Thanks. So I think basically the work I carried on also with people in the Loess community brought me to the general idea that basically clearly there are certain qualitative aspects that a Loess scientist would know very much, and this is understood. But then an important aspect for the specific efforts of measuring is having information from a site which is representative to the large scale. So for instance, Loess Terrace idea, from my understanding, it could be an idealized place. And also have information that allows to relate this to the general stratigraphy of the region. So knowing that, so this basically all increase the way or the confidence that we have that this is representative of on large scale. So for instance, maybe also another aspect which is important is trying to understand the link with the source areas for us, because we can evaluate or try to prescribe otherwise the source areas. And if we know that there is a link between the source and the sink, then we can use the latter to evaluate the former. And so I don't know, the size distribution is important. So somehow things like a transect from the putative source areas could be useful to imagine if, or to test whether these holds also compared to geochemical or other sort of provenance studies. These are all useful, and an evaluation also of the uncertainties clearly is an important aspect now, because basically all these come from the chronology, as also Gabor Uivari explained yesterday, essentially. And so clearly there are several dating techniques which are applied, and it's not obvious for me, for instance, which ones are better or not. So clearly there are also these aspects and that go in, and then which parts of the chronology you assemble to build the time series, which is also relevant. It's a complication of trying to look at the time series compared to just a general glacial or last glacial maximum time slice. So is that maybe that could go along with certain variation in other aspects of the profile, other proxies.
Okay, thank you. Beside the Loess committee, do you think we should use some, such as the high-speed camera or the satellite, to observe the dust properties to impact the climate? What is the important work we should we do? What's your comments?
Yeah, that's a very good question too. I think it's also very important to have modern observation of dust. In particular, I think of dust deposition close to the source or to the sink areas. So it would be nice to have, when you have a loss sequence, to know what's the current status of dust deposition, whether it's dry or wet deposition, the proportion of those, so the mechanism, so we can also compare in our model because this is a data which is missing in general. It's very poorly constrained, and it would be also particularly important to have close to where we have measurements of the position of the past, so we can try to link the present and the past, which is a difficult task. So that's indeed a very good, it could be a very useful thing to have.
Okay, thank you very much.
Is there any other question? I'm not sure if Chen Yuanqing asked question or not. No, if there is someone who is willing to present their own data, it's also okay because we are like interactive discussion part. So you are welcome to present your data here, and we can discuss and communicate. I actually also have some questions. Actually, I prepared some questions to want to communicate with you and others. Because I will share my screen first. Can you see the questions?
Yes.
Yeah. Because I make a count, and we have like 125 abstracts in the Loess Space conference, which will be held in the weekend. But only 6 of them use numerical model in the abstract they mentioned to study climate change. I'm not sure whether they focus on dust, but it's clear that there are less modeling studies in our community compared to the experimental study in the field. So on one side, we know the Loess is very important archives to reconstruct the depositional processes of dust. But on the other side, it's really important. And also, I think you mentioned how to combine dust modeling studies with Loess, with all other archives, geological archives. So from your perspective, how do you think for us geologists, all geological archives can be better contribute to the understanding to the whole process, not only the depositional processes, but for like the emission and transportation processes of the dust? And like how can we improve the predictability of the model and how we quantify the effect? I think some of the maybe you mentioned, but yeah.
Yeah, I think that clearly the aspects also that, some of the aspects which are important for the, for instance, the provenance studies are also relevant for the mineralogical composition of the dust. They could be. It's as part of the many ways of looking at provenance studies, for instance, or these are. This could be also useful to understand, to constrain, because if you are able to constrain the source to the sink, you can, and you have information about then the mineralogy, you can improve somehow the way we represent mineralogy with what this implicates for impact with radiation, because different minerals will have different impacts on radiation, especially the iron oxides are absorbing, so they can alter a lot. Other are important for the processing also of dust and iron, and so the impact they have on biogeochemistry once deposited. But also I didn't mention that explicitly, but in particular certain minerals are thought to be important or relevant for the way they can act as ice nuclei. So knowing this in details so when there is enough data that we can incorporate this and validate this properly, this will also have this ongoing development in with all the cascade, I say, impacts, the possibility of cascade of representing the feedbacks on the climate system in all the ways, in all science. This is one aspect indeed, and then the link with the modern observation, whether when it's possible to have this, would be very useful, I believe.
So how do you think about the dust effect on climate system? I mean, if there are some quantitative study to show, like, for example, the interglacial cycles, some people said dust also play a role. So how much or how the degree? Do you have some comment on this part?
Yeah, I think that in general, the estimate could be that in between the glacial, interglacial, overall, the dust varied between 2 and 5 times more dusty in the last glacial maximum. Clearly, there are different archives. So ice cores are the ones that show the highest increase in the flux, maybe 25 in Antarctica, and less in the other area. So there are, but when trying to do this exercise of assimilating this data into the model, then you can have an estimate, and this is sort of the range. One thing that I would add, maybe it's not specific for the Loess community, but in a way, I feel that we have more confidence in knowing what was the amount of dust in the last glacial maximum than in the pre-industrial, which we don't really have. Also, is compared to present day to the pre-industrial, we have even less information, because the kind of archives that have the temporal resolution to keep this kind of information are different than the one traditionally used. So Loess, marine sediment. So clearly, if there were studies linking the present and the paleo in this sense, passing through the pre-industrial, those be very, very, very useful, because they are, I feel, almost completely missing.
Thanks. I'm not sure if there is other questions. You can also, there is a questions in the chat box. So the dust particle size composition is an important parameter. How to measure the parameter? Collect dust and measure it, or use other method? If you collect the dust, what instrument you usually use?
Okay, so it's an interesting question indeed. So I think it depends whether it's from a sedimentary archive. So usually, so laser diffraction is typically probably the most common used for, I think, at least in the Loess community and the marine sediment community, in part also in the ice core community. The choice of the instrument depends also a bit on the size range of the particles. So, for instance, in the ice cores, where you have generally smaller particles, it's also common to use a Coulter counter, which is more precise in a way because it measures the volume of the particle. On the other hand, optical properties like the laser have a larger size range. So that's why they're useful, especially for marine and especially for the Loess sediments, which spans a larger range. These can have some more uncertainty because they depend on the particle orientation somehow. So you can have some discrepancies. And there are also some studies trying to relate these differences with the particle shape, which are mostly from the ice core community, which could use both different techniques on the same. And this is mainly the techniques which are useful for the sediments, meaning that there are other ways, but these can give a high resolution, let's say, compared to the sieve and pipette method or these very coarse kind of subdivisions. If it's the atmospheric, so the dust deposition, and this can be used, of course, also for dust deposition collection in the present day. If it's airborne, then it's a different matter, and there are other techniques which are used. So those are the same that can be used for air quality measurement, for instance. So again, there are laser sensors that can be used for this and are used also in the field campaigns, or even some of the cascade impactors, which are used for air quality, for measuring PM10, etc., that could provide some information about these kind of issues.
Okay, we have another. Yeah.
Hi.
Sarah, please.
Yes. I am also one of these people who does paleo climate research with unfortunately very little experience in numerical modeling. But obviously we all know that the whole system is very complex, and it requires a lot of parameters that need to be taken in consideration. And in many cases, our access to this data is limited. So I know of some other climate modelings that it's possible to use reanalysis data when it comes to precipitation, wind, and temperature, and so forth. And I was wondering, is this something that could potentially be useful at all for also dust modeling? Or is there any advances in that direction? Because I guess there is many areas where we have very little information. So yes, that's my question.
Okay, so thanks for your question. So basically, typically when talking about the reanalysis data, we are talking about the atmospheric variables and wind fields in particular. So these are useful especially in the stage of development or testing, I say, of the dust scheme, because we can reduce somehow the potential biases in the model, at least concerning these kind of atmospheric variables. Clearly, then when it comes to running simulations, either of the past or the future, we need to rely completely on the wind. So this is, I think, using this reanalysis, atmospheric analysis, is a step of validation of dust schemes, as well as other aspects of climate modeling. Other than that, you're perfectly right that there are several limitations. So I mentioned one, for instance, of the soil maps that people try to use when developing the mineralogical composition. We have this FAO, the UN soil maps, and they clearly are not adequate to the level that we wish. That's why a mission will hopefully focus on a specific area which are much high spatial resolution in trying to identify at least some of the key mineral species. And this is one example, but this concerns also the soil grain size distribution, which could be important in relation to either the way soil moisture represented in models, for instance, concerning dust emission schemes, or for the more physically based dust emission schemes, also the representation of saltation and sandblasting, which depends on the availability, of course, of grain size in the original and the parent soil. So all these clear information are a limitation for the application of the schemes. And clearly, also, if we think about the other surface conditions which contribute to dust emission, clearly we can think of vegetation. We can know present-day vegetation with good accuracy from satellite. We can represent, there are ways this is represented in models. Clearly, for past climate conditions like the AGM, this is the more difficult to know. So it's all more difficult to know. So clearly, also other proxies related to loss or the environment where loss could help. I think of pollen data, for instance, foreign assemblages. So some proxies or information telling us something about the vegetation condition. And I would say for the emission or the preservation or the possibility of accumulation of loss, what kind of vegetation, for instance, it could be also useful pieces of information together to improve the way we can understand and compare with models. Don't know if I answer your question.
No, yes, thank you very much.
You're welcome.
So if there is no other questions, I'd like to close this session, and thank you again, Samuel, for your great talk. It's really
thank you very much for inviting me and for all the audience.
It's really important and relatively new for all of us, the Loess community. So, and thank you all for participating in this session. And I also want to mention that tomorrow will be the last day of our workshop, and Professor Hua Yu give us a keynote talk, and I welcome all of you to join us tomorrow. Okay, so thank you, Samuel.
Bye, thank you
all. Bye.
Thank you very much, Samuel.
Bye-bye.
Bye.